Okay, well, let's make a start. First of all, welcome everyone. My name's Jeff Eggleston. I actually work for IBM, but I'm chairing this meeting on behalf of GSE today. And we're very, very fortunate to have John Tickesy, I'm hoping I'm pronouncing that right, who is going to be talking about what SMF data tells us about Z mainframe internal usage. This session is 5H, and that number is very important at the end because we depend on feedback. We're a voluntary organization, and this actually helps us set the presentations for future events. So please, at the end, can you make sure you fill in the feedback, please? I've got nothing further to say except the floor's yours, John.
Yes, good morning, good afternoon. John Tissick is my name. I'd like to talk about an interesting topic for me. Let me share my screen and let's get into my presentation. So just a little bit about me. I'm based in Germany. I travel and I visit customers. I'm a technical person and I've been working with IntelliMagic and the software for quite a while. And you'll see some of the software being shown to show us some of the detailed information that I'm looking at. Okay. So just a short, brief view of the agenda. I want to have a quick look at the Z mainframes, a short overview, a very short overview. And my focus is really on the SMF data sources and what I'm specifically looking at. And I have some examples in the presentation. So I'd like to look at what we can see in RMF, SMF, in the mainframe utilization, internal utilization view. And then I'd like to do a small interactive session if time permits. And as has been said, please interrupt and ask questions as we go along. Yeah. So a very short overview, mainframes. Now mainframes, a little bit different to the way they were with the 360, contain various items, as you can see on the right-hand side. Processors, cache, of course, memory, of course, additional cards, PCIe cards with 500 infrastructure. So the mainframe is complex and has become more complex. And what I'd like to show you is just a very, very short overview of some of the mainframes I want to look at and the internal information that I'd like to look at that we can report on. So I'm just letting you know that there are many architectural changes between these mainframe generations, and I'm really only focusing on the few items that I can look at in the RF SMF data, okay? So I'm starting with the Z15. So the Z15 has, for example, an integrated accelerator for data compression, which used to be an external, or rather a card that you could plug into the actual mainframe with Z14 and previous. So data compression, internal accelerator is interesting to look at. There's an internal integrated accelerator for sort processing. Z Hyperlink Express interfaces are available. And what I'm looking at here is a picture of the cache structure overview. By that I mean we have the level 1 and the level 2 cache, which is per core. And then we have the level 3 cache on the chip, and then a level 4 cache per draw. And this is important information because this has changed going forward on the Z16 and on future architecture. So you can see a little bit on the right-hand side, a picture of the level 1, level 2 caches and how they're dedicated, if I use that term, and how the other cache levels are shared. So moving forward, Z16, accelerated, integrated accelerator for artificial intelligence, for AI, is something that's in addition to what I just showed you for Z15. And here the cache structure has changed a little bit. Namely, there's a dedicated level 1 cache per core and a much larger level 2 cache, which is actually shared and used for a virtual level 3 and virtual level 4 cache. Which means that when we look at the data, we have to be aware of this architectural change. And you can see in the picture on the right-hand side, the level 1 and the level 2, and the term virtual level 3 and virtual level 4, which used to be separate chips in previous generations. So as we've hopefully recently heard, Z17 is now announced. And what's interesting here is an on-chip data processing unit, which is incorporating I/O activity. That's a very interesting move forward. The second generation of the integrated accelerator for AI, and of course changes to the sizes of the level 2 cache, for example. So that's basically the architecture I'm looking at. And now what I'd like to look at is, how can we see the internal parts of our architecture, of our mainframes? So the main source that I would like to focus on for the hardware-related information is produced by the Hardware Instrumentation Services, HIS. So when that service is running on your LPAR, it produces SMF 113 records. And they contain a lot of very interesting information about the internal, for example, cache usage. Now, in addition to the 113 records, there are obviously records that RMF or CMF produce. An example is the SMF 70 subtype 1, which show us CPU and LPAR information, PRISM information, ICF activity, which is also, of course, very interesting to look at our workload at the hardware level as well. I'm also mentioning HyperDispatch, the SMF 99 subtype 14, also a very interesting subtype record to look at to see how our workload is executing on this architecture. But as I said, my main focus is on 113 records. So the hardware instrumentation services, you'll need to set it up, which means taking a look at the MBS system commands manual, chapter setting up hardware event data collection. And basically, a starter task needs to be defined. You then need to go into your hardware HMC and ensure that counter facility options, security options set per profile. That allows this data to be collected from the hardware. And of course, in your Palm lib SMF PRM member, you need to ensure that the 113 records are being collected and stored. Just quickly having a look at the starter task, very straightforward, top, and we can see once it's been started, it tells us that it's collecting data. Okay, so this is what you expect to see when you started this task on your LPARs. Okay, so the information that the SMF 113 subtype 1 contains is described in two manuals. And we refer to them as counters. So they're the basic counters, and I'll give you examples of both basic and extended. So the basic counters are in the manual load program parameter at CPU measurement facilities. And then there are the extended counters, which are architecture specific in the CPU measurement facility extended counters. Okay, so you really need to look at those two manuals to understand what kind of data HIS is gathering for us. So let's look at some examples. So based on the basic counter set, which means I'm looking at two counters, the cycle counter, instruction count, we can visually look at how many processor cycles per instruction, in this case per KEK for our hardware, for one single day. So what's interesting here for me as an observer is that the processor cycles per instruction basically during the day period between 8 and 5 p.m. is very consistent amongst the four KEKs. And it's different during the batch period. especially in the morning. And that's probably very typical for a lot of customers. On the slide, I've indicated B0, B1. That's the terminology we're using to indicate which basic counter we're looking at. Okay, so they're the two that we're looking at, cycle counter and instruction counter. And as I said earlier, these charts here are produced by the software IBM Z Intelligent Magic Vision for ZOS. So there's a lot of information here about looking at data also interactively. And if I have a chance, I will get into an interactive session to show you some of the information we can look at. Another example, now we're looking at the extended counters, specifically the Z16 architecture. So what we see here for 2 KEX is the level 1 data missed. Okay, so we've had a miss in the level 1 cache, and it's been sourced from off-draw memory. Why is that significant? Well, sourcing data into cache from very far away, memory off-draw, is going to cost you cycles. These are cycles that you're burning and your applications are not running. Okay, but the process is obviously using these cycles to get that data. So you need to be aware of how many cache misses you have and where they're being sourced from and how that's influencing your efficiency of your applications or of your workload. So just looking at this chart, we see, oops, one of these KEX, the blue one, is sourcing the level 1 cache misses from off-draw memory. That's going to cost extra cycles. And that's the counter, the extended counter, 159, that's used to look at this data. So that's just 2 examples, one for basic and one for extended counters. And as I said, you need to look at the extended counters for your specific architecture, Z15, Z16, etc. Okay, so I'd like to move to what kind of data can we actually look at? And I'm looking at some examples and what it maybe indicates and what it can be used for. So example 1, looking at extended counter 159. Level 1 cache missed and it's sourced from somewhere else. So as I said previously, these instructions are going to take longer because the data needs to be sourced, in this case, from a location which is relatively far away. So the further away it is, the longer it takes. So this is what we want to look at and potentially see whether we can firstly observe it, which we can, and whether we can influence it. So what's also interesting, this is the basic counter set, is, well, how many level 1 cache misses did we actually have? I'm looking at the same KEX here, those 2, and we look at how many level 1 cache misses, percentage. It's actually not very much, and actually both KEX are the same. So you have to be careful when you look at a chart where you may see huge spikes. It needs to be looked at with relation to, for example, well, how many level 1 caches misses were there in total, or rather percentage-wise? So what I'm trying to say here is use example 1 with caution. Okay. And here you see which basic counter sets are being used. So a term that we all know of is the relative nest intensity. How far out into the nest we have to go to satisfy our cache misses. So what I'm looking at here is the RNI for LPARs at an LPAR level. And it's based on basic and extended counters, and there are numerous of them. Now, the RNI by itself to observe is interesting, but it's really used not necessarily to indicate a performance issue, but indicate or to use together with the level 1 LM1P to look at the workload in order to match it to the LSPR workload for purposes of going forward with new hardware acquisition, for example. What is my workload really doing? Is it high, medium, or low, etc.? So that's what the RNI is interesting for. For me, what's interesting is to look at the difference between the different LPARs as well, different workloads and different definitions on the KEX. So staying with the RNI idea, when we look at this table here, we can see the RNIs in the relative nest intensity column. And we also see the workload category. So even though that RNI for that system D001 was quite high, the workload category is still an average workload. Compared with, for example, the LPAR T001, which has a workload category, LSBR category of high. So this is the kind of information that you want to look at based on the 113 data to see, okay, well, what kind of workloads do I have? And what do I need to look at going forward with architectural changes, new hardware, for example, for my workloads. And in addition, there's a column here which just shows you how many cores for the selected period are being used for this workload. So this is interesting for KEK upgrades. So this is an interesting chart, and the title is Store in Instruction Stream Invalidations, SIIS. So what we're looking at here is basically an invalidation in the cache because data is present when instructions are being executed, and all of a sudden the cache needs to be flushed, and that new, or rather that instruction data needs to be reloaded. So that's a very expensive cycle problem that we really want to avoid. So when we look at the cache invalidations, SIIS, we can see, for example, for one particular LPAR, compared to the others, okay, I'm only looking at one, a significant percentage of these invalidations in cache. And that's costing us more MSUs for this workload. And then the question is, well, why is this happening? Well, typically it's happening because it's older code being compiled with an older compiler. That's a very typical reason for this, which means identify, if you can, which tasks are suffering from these store and instruction stream invalidations, recompile or look at the code to see how you can improve if it's a very old assembly code, for example. So this chart is based on the extended and the basic counters. So what's also interesting based on extended and basic counters is looking at the breakdown of the transactions or the instruction cycles for where the cache misses are, or rather, how many cache misses and percentage-wise or cycle-wise in this case, and when the process is actually actively working for us. So what we're seeing here, for example, in red is the active working cycles for our workload. And we're then seeing in blue, actually the wait cycle count for this particular KEK. And you also see TLB misses, which is in today's architecture very, very small and consistent with that. And this chart really is very workload dependent. So this gives you an idea really basically, well, how much processor activity do I have and how much in addition is wait cycles, which you want to minimize, of course. So another example is referred to as a finite CPI, which is the delay cycles per instruction because not all data and or instructions are available in the level 1 cache or in the translation look-aside buffer. So we're looking at two LPARs here and on the same KEK. And clearly the blue LPAR Q002 has a higher impact of cache and TLB misses. It is suffering more than the red LPAR. So for me, as an outsider, the first thing I would say is, well, are we looking at two production systems? Are we looking at similar workloads? How can we compare these two LPARs? So that's an important point to look at. But let's just take this example further. And as you can see, it's based on extending the basic counters. So one thing we can look at, which takes us now away from the 113 records, is look at the RMF data, which shows us, for example, the processor polarity for these two LPARs that we're looking at. Now we can see clearly that the LPAR on the left, P002, has a much higher workload than the one on the right, Q002. What we can also see is the LPAR on the right, Q002, has peaks of activity that are running on not only vertical high, but also vertical low processes. Now, vertical low processes to us means potentially that work is running inefficiently. So this is an observation that we have for these two separate LPARs and their workloads right now. And what's interesting here is, okay, can we explain why this is happening for Q002? And then, of course, what can we do about it? So my last statement there is probably the Q002 workload is using more resources than defined for those peaks. And quite often we define resources for the activity across a day boundary rather than for a specific peak. So sometimes this is actually understandable. Sticking with RMF data, we're now looking at a chart which is showing us the general CPU usage relative to the LPAR weight. And the reason I'm showing this is that we define our LPARs on the KEC, we give it a certain weight, which means it has a relative weight to the other LPARs, and we assign processors, logical processors. And based on that combination, we get vertical high processors, medium and low processors. So what we can see here is that the Q002, those peaks that were running on vertical low, are actually bouncing up to 160% of the LPAR weight. So this is an indicator of what's running on this LPAR is more than what we planned for in the configuration. This may be what we want. If it's production, we don't want this. If it's continually above the 100% line, we need to look at why it is. So this is a very nice chart to have a look at what our workload is doing. And again, this is based on SMF data, data from RMF. So we can go a little bit further and look at what we call engine dispatch analysis for these two LPARs. And on the left, you can see the P002 LPAR. The red line is the dispatched time for the processors. And you can see the processor physical share, the LPAR processor physical share, the green line. Our P002 LPAR does not reach the physical share that's been defined for the LPAR, which means there's a little bit of room for growth. Let's use that term. If we look at the Q002 LPAR, those red peaks, which means the workload, is bouncing over the physical share, i.e. more than what we've defined. What that means is that that LPAR is going to be suffering from more cache misses and having work running inefficiently, because other systems are using the cache as well. It's a shared processor. Okay, so when we've looked at the engine dispatch analysis for that one LPAR, let's look at the instructions executed on processors, number of cycles per instruction. And we can see that the peaks match the peaks in the bottom chart match the peaks in the top chart, okay? We're using more instructions, most likely because we have more level 1 cache misses, i.e. more cycles per instruction needed, sorry. Okay, and this is showing us that our workload is inefficient. It's using more cycles for the same instructions. And as you can see, it costs money to do that. And we do want to minimize that if we're talking about a workload that's important for us. When we look at level 1 cache misses, again, now we're back to the 113 records. We can see these two LPARs again, the large LPAR P002, which was running efficiently with its processor definitions, and the Q002, which had its peaks. And we can see in that light blue category that some of those cache misses were sourced from the memory on the module, for example. So what we can see here, based on the 113 data, is when there are cache misses, where it's being sourced from. So clearly the Q002 is sourcing its cache misses from areas further away from the level 1 cache. Okay, so that's what this chart is showing us. It's only an estimate, but it gives us a good idea what's happening between these two LPARs. So that was looking at level 1 cache and cache misses and instructions. There are many other things that are available within the hardware that we do sometimes want to look at. For example, we're using the Nest accelerator for compression. How intensively are we using it? So this kind of data here that we're looking at, synchronous calls, is reflected in the extended counters per architecture. So we can certainly see that we are using that accelerator unit and in how intensively we're using it, and for what purpose as well. Another thing that's available in the architecture is the integrated accelerator for Z-sort. So where it's being used is from something like DF-sort, if it's been enabled, and from DB2 internal sorts. So what we can observe here is this integrated accelerator in the hardware being used for sorting or not? That's a very nice piece of information. If we think we've turned it on, we can certainly verify if it's being used or not. And we can see how intensively it's being used. So good instructions, good information here based on the extended counters. Another interesting internal accelerator is the artificial intelligence accelerator. And unfortunately, it's very hard for me to find a lot of good data to show you. But what we can see here in this very, very simple, small example is, yes, it is being used. Okay, and we can see calls per second for these instructions. So this data is available in the extended counters if you're moving towards using the accelerator for artificial intelligence. You can observe how intensely you're using it. And of course, we're encrypting our data, I hope. So the coprocessor is one option for encrypting data. And what we can do based on the basic counters in 113 data is look at what percentage of time is being used from the core for crypto functions. So in this case, it's very, very low. But we can look at, to some degree, what type of encryption is being implemented at the coprocessor level. Okay. Now, there are crypto express cards, which are separate entities, which can be reported on via RMF as well. Yeah. So another example of the crypto coprocessor, we're looking at basically the percentage breakdown rather than that previous chart to see how intensely that coprocessor is being used for this kind of work. And this is based on SMF data now, but rather RMF data that is stored in SMF. So what we can also see from RMF is data about the PCIe usage. And what we're looking at here is basically operations per second for these function IDs that are defined on these on this KEK, on a single KEK. So this is again internal information which is useful, gathered by RMF rather than the HIS task. Okay, I'm hoping that that's given you a taste for what kind of information you can look at. I'd like to just quickly interactively look at a few charts. We have a little bit of time. And please interrupt me if you have questions. Let me just stop sharing and share my other screen.
Again, everybody should be able to just come off mute now. I've disabled it, so just go ahead and be interactive.
Okay, thank you, Jeff. Okay, so what I'm looking at here is a web browser view of the data, which is stored in a database processed by IntelliMagic Provision. I've created my own dashboard just with some information here. But what I'd like to show you is the screen cache invalidations here based on stored instruction string, because this is, as I said, something very interesting. So what this is showing us is in this particular system, LPAR, we have a lot of cache invalidations due to the instructional data needing to be flushed and then reloaded. And as I said, typically because of older code needing to be compiled together with the new compilers or very, very old assembly code. Now, the 113 data, and you can see in the bottom here where we've described what data it is, shows us only the cache invalidations per interval for the KEK here. There's no information about which address space is causing this, which is unfortunate because that's what we really want to do. We'd like to be able to pinpoint, aha, this is the guy we need to look at. What kind of code is that? What kind of compiler is it? That's to recompile it. So that data is not available in the 113 data. But SMF30 actually gives us a little bit of assistance. So using our software and doing what we call a drill down, I'd like to drill down to the address spaces at or around that time. So in tabular format, what I'm seeing is the address space names based on the SMF30 data, address space information, and cycles per instruction. Now, this is not telling me who is suffering or who's causing those cache invalidations, but this gives me a very good idea of who's burning a lot of cycles per instruction and where I should look first. So when you do see that in your installation, then it's worth looking at the SMF30 data to see if you can pinpoint or have a small subset of address spaces that you need to look at the workload to see whether they do need to be recompiled, okay? So it's very interesting information. So let me just go back to where I was. So I just want to look at a couple of charts here. Engine dispatches. Actually, let me look at something slightly different. We were looking at the estimated impact of the cache and the TLB misses, and we were talking about the P002 LPAR and the Q002 LPAR. And what we were saying was, well, let me do a full report here. The big LPAR on the left, most of the workload vertical high processors, that means efficient. Very, very little workload on mediums and lows, which is different to our smaller LPAR. We have a chunk of work running on vertical mediums and actually some on vertical lows, which we have a quick look at by time. And here we see those peaks. So just to explore our hardware topology, what I've done is taken a look at the topology of this KEK, this hardware, with all of these LPARs based on SMF data, okay? So when this changes for whatever reason, because you've made hardware changes, or you've changed locations, etc., you can see where these LPARs are running as far as their processor polarity. So this is zips and CPs showing us chips, clusters, etc. But let me actually go back and limit this to this chart here. So I'm not only looking at the CPs, I've ignored the zips in this case, and I'm only looking at those two LPARs, or rather I'm looking at two other LPARs here. This Q002 LPAR, this is the one who's suffering, and I'm only looking at the vertical lows processors here. And they're in this chip on this cluster. This LPAR is sharing that chip with this LPAR here, N002, which we haven't seen before, which has vertical highs, medians, and lows. So this LPAR here is getting preferred treatment, if I can use that term, for the cache on that particular chip. Let me just go back to where I was quickly to make sure we understand what we're looking at here. Let me go to the big picture. Q002, we can see that one processor is here, this vertical high, and this is where the vertical medium and low from that system is being used. So what we can do here is look at which other LPARs and their processor polarity and their processor usage is being used for that chip. What can we do about this? Well, if it's an important LPAR, we can look at, for example, the LPAR weight. We saw that the relative weight was potentially something we could look at. And of course, potentially the number of processors, logical processors. Very dependent on what kind of workload you actually run on that LPAR. Okay. Okay, so I'm not sure whether I should continue with the online demo here. Let me go back to my presentation. If there are any questions, please interrupt. So let me just share my slide screen again. So we have a Z17 architecture, which is now available. So I'm not going to focus on a lot of things in Z17, but one item, which is interesting and new, is CPU power consumption. So what that means is that the power consumption for various categories of information, as you can see in the legend, power consumption, unassigned infrastructure power consumption. Let me go to one next chart. Storage power consumption, I/O power consumption. These kinds of pieces of information can be viewed in RMF for the LPARs and the KEC for the Z17 architecture. So this is very new and interesting information that is being reported and can be quite useful for comparing power consumption and potentially for other billing purposes. Let me leave it like that. Okay, so this is around the corner, which is good to see. Okay, Jeff, I think I'm at the end of my presentation, unless there are any questions. I'll pass it back to you.
Okay, thanks, John. And any questions from anybody? You can put them in the chat if you don't want to talk. I'm going to feel like an auctioneer then, but before I do, I'd just like to remind everybody that this is session 5H, and thank you. You can read my mind, John.
Yes.
The feedback is important, and we'd welcome some feedback on this. So please, can you give it? I've got to say, from my own personal point of view, one of the messages that came out loud and clear for me on your presentation was what older code can do, particularly with your bit about cache invalidations, sort of bringing out that point. And the second point I'd bring is I was quite surprised how simple your graphs are, to be honest. Very, very nice and simple and straightforward to see. So, John, it's been a fantastic presentation. I'm going to I think somebody's just said something in chat. Oh no, you've blown somebody's mind, John. That's what it said. So
well, that's quite good. Thank you,
Charles. So I'm gonna be an auctioneer. I'm gonna say once, twice. Okay, no more questions. So I'm gonna bring it to a close. I'll finish off by saying, John, fantastic presentation. Thank you very much for your support.
Thank you very much for having me as well, and thank you to the audience as well. Okay.
Okay. Thank you very much. Cheers.
Okay. Cheers. Bye-bye.